that far. All right, Jaden, is this what's on your screen right now? Mm-hmm. Okay, let's set that window. Let's set the window to what that picture shows. This picture here. This is your axis. Okay, so Jaden set his window from 0 to 10, and then on the x's and 0 to about 300 on the y's, and so it seems so it looks pretty similar. So what did you have for question 1? What mathematical concept would tell us the distance from yesterday? Yeah, it was area. That's right. That is a mathematical concept, and that's what we're talking about here. I don't remember if I said it. I think I might have. It was in exploration 3. Actually, it was in bold if you just flip back one page. The definite integral. Yeah, the definite integral. And again, that's something we're going to talk about, to the second half of the year. So this is just a little bit of a continuation of what we did yesterday with that area. Okay, so we've got a velocity graph here, elevator, nice, and a rocket, but we've got her velocity. Okay, and so it makes sense that if we could do the area underneath there, that we could figure this out. Okay, so we could figure out how far she's traveled. Now, they're talking about from 0 to 8 seconds, so 8 would actually be right here. Okay, so we'd really be talking about this area right here under there. Okay, so what did you get? It said estimate this. So what did you get in question 2? Anybody? How many squares you got there?
I like 60.
61? Yeah. Okay. And each square is 25 miles. So what is that? 1,000, and this was in miles. Okay, this was miles per minute, wasn't it? So 1,525 miles. So that's this area under here, counting squares, right? Counting squares. All right, so that'd be one way to get the area. But what would be another way to get the area is the problem in this worksheet. So, so when we've done these explorations, we're trying to look at the big picture of what calculus is going to be about. And so far, I think if you could summarize it, it's we want to do something with changing quantities. We want to find an exact instant. We want to find an amount of some changing quantity. And the dilemma is because it's changing, it's hard to do. So we couldn't do, so when the door was swinging open, we want to know how fast the door was opening right at 1 second. But that's hard to do because rate of change, we need 2 points. Average rate of change, we need 2 points. Slope between 2 points, we need 2 points. But we wanted 1 point. So what did we do? We picked 2 points really, really close together, right? And we did like an estimate. And we got it really, really close together to get a better estimate of what's going on. And then the same thing here. We figured out that if we do the area underneath this curve, we could find how far that thing had traveled. But the problem is, that's not a geometric shape. That's not something we know how to find the area of. There's no formula to find the area, so all we can do is estimate, right? So then the idea might be, how can we get better and better estimates? Well, what we did there was pretty rough. We just counted squares, so how much is that? And we added that with that, and that's pretty rough, okay? So how can we get better? Well, so this is what they're going to have you do. So in number 4, it says, divide the region under the graph from 0 to 8 into 4 vertical strips of equal width, okay? So what they mean, and now so if it's 0 to 8, you want 4 of them, how wide is each one? Each one is 2 wide, okay? So right? like so. Those are my strips. Now, it says, draw 4 trapezoids whose areas approximate the areas of these strips and whose parallel sides extend from the x-axis to the graph. So, what's a trapezoid? Well, normally we think of a trapezoid as one pair of parallel sides, but the others aren't parallel necessarily, right? That's a trapezoid. One pair of parallel sides is a trapezoid. Okay? Well, in calculus, the kind of trapezoids we're going to draw are going to typically look like this. They're going to extend vertically. That's also a trapezoid, isn't it? Right? It's got one pair of parallel sides. Okay? Well, that's the kind of trapezoid they're wanting us. That's what they're saying we can draw. So, in other words, what they're saying is, if I could do this, so I've got, the bottom here, and then if I connect with a straight line, this point to this point, and then connect this point to this point, and then connect this point to this one, and then connect this one to this one, I would have 4 trapezoids. Make sense? Okay? Now it's possible this second one is a rectangle. It's possible that that actually goes straight across there, but it doesn't matter. Doesn't matter. Okay? So what's going on? So the idea is very much like we do with slope. We don't know how to find the slope of one point, but we can estimate that slope by picking 2 points really close together because we do know how to do slope with 2 points. We don't know how to do area under this curved thing, but we do know how to do the area of a trapezoid. So how about we split it up into 4 trapezoids? So if we did each one of those trapezoids, okay, so now what we're going to need to do, and what's it say here? It says, by finding the areas of these trapezoids, estimate the distance L goes. So we need to find these points. So go to your graph on your calculator, and let's trace, okay? So what is this point right here at 0? 110, okay? And then what's this point up here? This would be 2 and 234, and this one would be 4 and
38.
How much? 238. And then this one would be 6 and
170.
170. And this one would be 8. 78. Okay, so there you go. So now what's the area of a trapezoid? So 1/2, then we add up the parallel sides, right? The 2 bases. Now where are my parallel sides? Those are my function values, right? Those are my y values, right? So we'd add up 110 and 234. So 110 plus 234, and then times what? Remember the formula, half B1 plus B2 times the height. What's the height of these trapezoids?
It's the bottom. Yeah.
It's this 2, right? It's because what we have is a trapezoid tipped up on its end, really. And so the height of the trapezoid is actually this distance right down here, which is 2. Okay, oh, that's easy. Well, the 2 is going to cancel the 1/2 in all these because they're all 2 wide, right? So really all it's going to be is 110 plus 234. And then what? Plus, we have to use 234 again, right? Because it's in, 234 is in this trapezoid and it's in this trapezoid. So 110 plus 234 plus 234 plus 238 plus 238 plus 170 plus 170 plus 78, right? Isn't that really all we need to do? Because in every one of the trapezoids, the 1/2 and the 2 are going to cancel, and so that's going to be, so we're just going to, so to add up those trapezoids, just be adding those up, right? What do you get? 1,472. Okay? Now, that's less than we got when we counted squares. Okay? What could account for that?
You didn't account for that area that we, like at the top.
We got some missing area right in here, right, where it curved. Because this is, these lines are straight, and I kind of exaggerated them. But this is curved, so that has a name, actually, we're going to talk about later in the chapter. It's concave down. We call that concave down. It's curved like this. So it's going to curve up over top of those lines. So there's going to be some missing area we're going to have there. And then, of course, counting those squares is iffy anyway, right? I mean, so who knows how real accurate that was. But it makes sense that this would be a little less, maybe, okay? Because we're missing some areas. So, all right, so let's move on. So there's an idea, right? Let's do something we do know how to do, which is trapezoids, and let's estimate the area that way. Okay, the technique in problem 4 is called the trapezoidal rule. Put a program into your grapher to use this rule. The function equation may be stored as y1. The input should be the starting time and the end, blah, 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 blah. Okay, so I've got a little program here that I made that I'm going to send to you at this point. I think I can do it while we see our presenter. Let me pull this up. There it is. And all right, look on your calculator screen now. Okay, now careful here before you do anything. It says, okay, transfer complete, all files have been transferred. We don't want to open typically, well, yeah, typically we probably can, but I want to show you how to get to it, okay? So let's just choose okay. Just choose okay, all right? And then then it kind of goes away, and so it transfer that. So let's go to the home screen. Everybody go to the home screen, and let me show you what happened there. When I sent that to you, it created a folder on your calculator called AP Calc Block 1. So if you go to My Documents over on the right, we don't go into here very often, but whenever I do send something to you, that's where it goes. So if you go to My Documents, okay, you go to My Documents, under My Documents you see AP Calc Block 1. Now you see a few other things that are normally in there, or they're in there. It depends if you have one of my calculators versus your own. You may have had some. So if you go ahead and open up the one I just sent you, which is Exploration 4, okay? Now, did it open up to this page right here when you opened it? No, it opened up to this right here, right? Okay, so be careful, don't mess with anything in there, or else it's not going to work, okay? And if you notice, I've got the equation written in here, and a few of you guys took my programming class last year, so you might recognize a few little things in here. But basically, this is, so in a document, okay, so we've been spending time in the scratch pad. In the document here, the way you can go back and forth is if you hit Control right arrow. If you hit Control right arrow, then that can take you to the next page of the document. You can also try to hit these little arrows, but that's kind of hard to do. But if you just go Control right arrow, Control left arrow, okay, you get from page to page. We don't need this to be on this page here. If you want to scroll down through the lines, you can see what we're going to do. We're going to, when we run this program, it's going to request a starting ending point, how many trapezoids you want. Here's my height. You know, how do you calculate the height? Well, B minus A is going to be the starting and ending point divided by how many we have. So that's going to be the height of each one. S is going to be my counter here, and then this is called a loop. This is a for loop. Actually, S is not the counter. S is our sum. We're going to add up these trapezoids. So S is for sum. So we're going to let S be the total, what's in S, plus each trapezoid. You can see how I get this. This is F of 1, which is the height, right? The heights, the B1, the B2 are those Y values, function values. So I get the first function value, then I get the next function value. That's the I and the I plus 1. So I get those two function values together, add them up, divide by 2, times it by the height, add that into S, and then this for statement just is a loop that will just run through, and it'll do all of the trapezoids, and it'll just run through there, and it'll add them up, and then it'll display it for us, okay? So that's the idea. That's what that little program is going to do. So we can do, instead of 4, we can do more than 4, right? So everybody do Control right arrow, go over to this page over here. I've already typed it for you. Did it show up like this on yours? Yeah. Okay. So if you want to run a program on the calculator, just go onto a calculator page. So that's what this page is. It's just a calculator page. And I typed Explore 4, and it bold-faced because it recognized, oh, okay, that's what he called this program. If you go back into this other page, you can see I defined it to be that, right? That's why it's there. Okay, but anyway, now hit Enter. If your cursor's out on the edge, just hit Enter. Okay, and it pops up this little request box, and so we're going to start ours at 0, so hit OK. And then does yours say 8? Yeah, it's probably because it's been run last time I ran it. I did this so it saves a previous value. So, and that's what we want. We want to go from 0 to 8. And I don't want to do 1,000 yet. Let's do 4 so we can check our work from before. So we hit OK. Okay, and there we go, 1472. That's what we have. Nice. Okay. Now, if we just hit enter, remember on a calculator screen, whenever you hit enter, it just reruns the last thing you did. So if we hit enter, it's just going to rerun the last thing we did, which was explore 4. So it'll run it again. So we can go 0, and there's 8. And this time let's do, say, 10 trap. Oops. Let's do like 10 traps. Okay. Oh, 1,512.32. So now we're getting closer to that 1525 we had. So what just happened by doing 10 trapezoids?
What area was it coming from?
Because of that red area, right? That red area we were missing. We're still missing some there, right? Because this thing's curving over top, but it's getting better. It's getting better. Let's run it again. 0, 8, how many?
1,000.
Just jump right to 1,000, huh? Okay, jump right to 1,000. Okay, so you do 1,000. Now imagine what that would look like, right? 1,000 little skinny trapezoids. Not a lot of fun to count by hand, but a simple little program like this. What was that? 10 lines, 12 lines, whatever. Boom, 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 runs through there, adds up those. So you look at those numbers, and maybe anybody do a bigger number? Do 10,000. See what happens. At some point, we're going to be limited by our decimal places, probably. Okay. So you have any thoughts on that area? Is that the exact area right there?
No.
10,000 trapezoids? Is that bigger than the exact area or littler?
No.
It's littler. We still have little tiny pieces of red up there that we're missing, right? But man, they're getting tiny. Do you have any thought of what the exact area might be? You think it's 1520 exactly? Well, not right now we can't, but I feel pretty good about the fact that it's 1520. Okay, now it's a pretty simple equation. And I'll just tell you it is. It's exactly 1,520. But you're right. This is going to keep getting bigger and bigger and bigger. But the fact that it just keeps going 99999 out this way as it gets bigger and bigger, right, makes me feel pretty good about the fact there's a ceiling on that. There's a limit of where that's going to be. We're going to talk about limits later in or early chapter 2. But that's what's happening. It's the same thing that would happen when we were doing that slope. If we picked 2 points, remember we wanted to find the slope at 1, so we picked 1 and 1.001. If we kept getting them closer and closer and closer and closer together, we would start getting closer and closer and closer and closer. I don't know if you remember, we were getting 30.6 something, whatever was our speed of the door opening. You would start to see we'd be getting closer and closer and closer, and all of a sudden decimal places wouldn't be changing. It's way out here. And so we could tell we had an exact answer out to 2 decimal places or 3 decimal places, however many decimal places we wanted, because they were never changing. Only ones changing were way out there. So even though we couldn't get an exact answer, even though we were estimating, we could get an answer as exactly we wanted to. That's the big concept behind most of what you're going to study this whole year, right? That's kind of the underlying thought behind what's happening. And then, of course, a big part of it's going to be how we can then use those results of what we got. Okay? So there you go. So keep going here. A couple other questions we can answer out of this on this packet here with this graph. So we did that. It said use 20. Don't worry about it. You can go ahead and do that. 20 trapezoids. What is that? We didn't try 20, but what would it be with 20 and so forth. Now, number 7 is a mouthful, but this is where it talks about the exact value of the definite integral. It says the exact value of the definite integral is the limit of the estimates by trapezoids as the width of each trapezoid approaches 0. Now, when we define the definite integral, we actually won't use trapezoids, we'll use rectangles. Okay? Because we do rectangles too. Now, trapezoids are a little better. You don't need as many, but it doesn't matter. If we're gonna do a million, an infinite number of them, it doesn't matter, right? We'll eventually be able to to get enough of them that we'll be able to see where it goes. So, so we did that already in 7. Make a conjecture about the exact value of the definite integral. That's 1,520, we thought. Okay, now this is a different question. So now this is something, again, on the next quiz. This stuff with definite integral and area, that's not going to be on the next quiz. Okay, that's big picture looking ahead. But what you are going to have to do on the next quiz is be able to put a graph in your calculator, be able to trace, be able to answer some questions. So if I gave you this problem, told you that this was her speed in miles per minute, and asked you some of these things, I'd want you to be able to do this. So, question 8 says, what is the fastest that she went? Okay? What would you do on your calculator to find the fastest that she went? I would go trace. Let's see, Jaden's tracing up here. Find where the peak is. Is it right at 3? Keep moving your left and right arrow there. There you go. There you go. That will, when you trace, if you just hit your right and left arrow, there are certain special values that the calculator will get for you automatically, and one is a maximum. So the maximum is actually right there. Okay? And so if you trace, it'll hit it exactly. It'll find it as you go by it. And so you got to go kind of slow and give it time to pop up. Okay? So the fastest she went is 248.021 miles per minute. Okay? So you can answer that question. So I want you to be able to do that. Now later when we get into, again, when we learn some calculus stuff, we'll be able to take a function like this and we'll be able to find that maximum by using calculus techniques, and it won't be good enough to just trace on a calculator and find it, according to that, right? As a matter of fact, I think in that course description book, it specifically said that, using the calculator's maximum finder is not, won't be good enough. But it's not hard, so you'll be fine doing the calculus part of finding it. Okay, next one. Oh, and at what time was that? 3.04189, and remember 3 decimal places. So you need to understand units, and that these are the minutes, and those are the miles per minute, and so forth. Okay? What was her rate of change of velocity when t equals 5? What are they asking for there? Rate of change. Slope. At 5. So Jaden, let's trace over to 5. You're in trace mode. Yeah, just hit 5. We want the slope. What they're asking for is the slope right there. And it says approximately. So what are you going to do to get that? Let's pick 2 really close points, right? Let's pick 2 really close points. Now, if we're going to use our calculator to help us out, here's what I want to see on a quiz. So let's go ahead and hit the scratch pad button there, Jaden. Let's go to the calculator here. Now that function is stored in F1. So I think the best thing, the quickest way to use your calculator, now you wouldn't have to, you could trace. What do you want to use? 5 and 5.001, a whole bunch of 5s, a whole bunch of zeros, that'd be great. You could go 4.999 and 5. I don't care, right? Let's say we did 5 and 5.01 or something like that. You could type in a 5, trace, write it down. You could type in a 5.01, hit enter, write it down, do your slope. That's fine. I don't care how you do it. But one way you could on the calculator here is you could type in you could type in F1 of 5.001 minus F1 of 5 all over 5.001 minus 5. I'd like for you to get the habit of thinking of slope this way, okay, as this difference quotient, all right? And you could just do that all at once right on the home screen, and you could actually type that in. You could write that down as your on your quiz, too, if you were doing the slope. I want to, usually when you're doing a rate of change of slope, I want to see your calculations. I want to see what you're doing. Even though you'd be using a calculator maybe, I'd want you to be writing down those points. Now, if all you did was trace and write down the points, that's fine as long as you put them on your paper and show me the calculation you're doing. Okay? Always important to show me. If you use your calculator to do a calculation, It's important to write out the calculation that you're having the calculator do. Okay, now let me show, yeah, he's going back and using parentheses. I showed block 2. I don't think I showed you guys. Go ahead and finish it out here. -5, yeah. So you're subtracting your y's, right? Because that's what this is doing right here. These are the y values, and then those are the x values, right? And there's your slope. So hit enter.
Can we actually grade F1 like on our paper?
Now, that's a great question. I would rather know if whatever this function, if the function's been defined in the problem, to be honest, the function's been defined as v, hasn't it? Over in question 3. So no, I don't want you to put F1 because that's calculator syntax. And remember, we talked in the course description book about that. So I was writing it out F1 because that's what I wanted Jaden to type. But on your paper, if you're going to use the function notation, which I encourage you to get used to doing because that's what we're going to be looking for, you would want to have typed it this way.
Okay,
Does that make sense?
Yeah, we don't have to actually give the point. We can just like write V of 5.1.
Right. V of 5.01 minus V of 5. Now, if you want to, again, trace, get that actual y value, and then write it out over here, that's fine. You always have to have your final answer to 3 decimal places, but you don't have to write out all the digits when you write it on your paper, your calculation, right? If you want to round and be short there, I don't care. But make sure when you actually are typing it into your calculator, you better use more than 3 decimal places. If you want your final answer to be accurate to 3 decimal places, you better use more than that in the calculation, because you get into rounding error. So that's very important. That's why I like this, because this is going to bring all the decimal places with it when it does the calculation. So I really would like to get used to using function notation when you do this stuff. Okay, so we're getting this, which kind of makes sense, because if we look at that graph, right, down here at 5, that would be this slope right here, right? We just found this slope of that graph right there. What does that tell us? What would be the units on that? What would be the units on that? See, this is something I want you to be able to answer on a question. Would it be miles per minute squared? What are these units here? What are these down here? What did we just do? We divided. We took the y's divided by the x's, right? So we were talking the other day how when we did area, we took miles per minute times minutes. See, this worksheet's kind of putting it all together now. Miles per minute times minutes, that gave us miles. That was the distance you traveled. That was the area. Now we're doing slope. So we're doing miles per minute divided by minutes, which is like multiplied by the reciprocal, right? Miles per minute divided by minutes would be like miles per minute times 1 over minutes. That's miles per minute squared. What is that? Physics people, that's acceleration, right? What we did is the rate of change of velocity. That's what acceleration is. It's the rate of change of velocity. That's what acceleration is. Now, I'll be honest, I prefer miles per minute per minute. It's the same thing, because that's more indicative of what's happening. It's the rate of change of your miles per minute. So it's your miles per minute, okay? Miles per minute, but it's the same as mile per minute squared. I'll take either one of those as units, it's fine. Miles per minute, or miles per minute squared. All right, was she speeding up or slowing down? This is really tricky, the idea of speeding up, slowing down. Why are you saying slowing down? Because it was negative, right? That's what people always want to do, and that's not the acceleration being negative does not by itself tell us if it's speeding up or slowing down. Okay? Take a look at this graph. What's going to determine whether it's speeding up or slowing down? Let me do this. Okay, here's the point we're talking about right here, right? If I've got a velocity graph that's going like this, and then let's say it switches to doing this. Okay? In which part, this is my velocity graph now, right? So the velocity, how do I say this? The velocity you're right, the answer is slowing down. However, it's not because this is negative. Maybe we should save this for another day. No, with that, we're into it. What's the acceleration of gravity? So this was an acceleration, right? Miles per minute squared. What's the acceleration of gravity? Negative, right? Negative 9.8. Why is it negative?
Because it's going down.
Because it's going in this direction, right? So if I throw a ball in the air, right? If I throw a ball in the air, as soon as it leaves my hand, it's going up. What's its acceleration? When I throw a ball in the air and it leaves my hand, and it's now the only thing acting on it is gravity, we'll ignore wind resistance, friction, stuff like that. But it leaves my hand, it's going up in the air. What's its acceleration? Negative 9.8 meters per second squared, right? Its acceleration is gravity. That's the only thing acting on it at that point is gravity. So when I throw it in the air, it's going up. Its acceleration is negative 9.8 meters per second squared. Is it slowing down or speeding up? Slowing down. Okay, now it gets to its peak, right? Starts coming back down, right? It's on its way down. What's its acceleration? Negative 9.8 meters per second squared. Its acceleration is negative 9.8 that whole time, right? Its acceleration is negative 9.8 the whole time. As soon as it leaves my hand, its acceleration is negative 9.8. But on the way up, it's slowing down. On the way down, speeding up, right? So it's got a negative acceleration the whole time, okay? But its velocity has changed, right? On the way up, its velocity is positive because it's going up. On the way down, its velocity is negative, okay? So the only way to tell if something's speeding up or slowing down is you have to look at velocity and acceleration both together. They have to be acting together. They have to be acting in the same direction for something to be speeding up. So if I throw a ball in the air, its velocity is positive, but its acceleration is negative, and they're working against each other, it's slowing down. Okay, that's what we have here. We have a positive velocity, and we have a negative acceleration, right? So that's why this thing is slowing down. Now, actually, you just look at the numbers, right? It's going from a peak of 200 and whatever miles per minute, and it's on its way down to lower numbers, right? So, I mean, you could talk about slowing down just that one. But not because that number's negative. Only because it's paired with a positive velocity, okay? If you have a negative velocity, remember, velocity has to do with direction, and we're getting a little far out into velocity, which we're going to have to do because we're going to do a lot of work with velocity acceleration, okay? So don't worry too much about that for the next quiz. But the thing to focus mostly on here is this idea of rate of change, right? We can do rate of change of distance, so we could get miles per minute, but we could also do rate of change of that. So we can do rate of change of velocity, miles per minute, and so forth. Okay. And then it says, at what time does she stop? Well, you can just trace along until it's zero. Is it abruptly or gradually? Well, it depends on your calculator where it crosses. So I guess we could just answer that real quick, Gene. So let's go back to your calculator screen. Hey. Say hey. Say hey, son. Oh, never mind. Missed it. Go back to your calculator screen. Okay, and now let's just trace. Let's just trace. Go out to 10. You're still in the trace mode. Go out to 10. And then right arrow. Keep right arrowing. It says, at what time does she stop? Well, that'd be when her velocity is zero, right? So we go down, right there. Okay, so that's another one of those important points that it will find. Now, did she stop abruptly or gradually?
Gradually.
Looks like fairly gradually, right, as it goes along. Okay, so those are just some things with reading off of your graph that are kind of important. Okay, let's, I want to leave you some work time here. So let's go ahead and get your notes out, and we'll talk about some exponential and log stuff here again real quick. And then I'm going to leave you with some time to work here. All right. Yes.
My computer froze a while ago, and I don't know how to make it. It just has like a little.
And it's been doing that for a while.
Oh.
What did I do? I kind of hit the on button.
I tried that. So thank you.
Magic touch. I don't know. So now, yeah, you try to go back to there. What were you doing? Do you remember when it happened?
It was like that program.
When the program was going? Okay. Did you try like 10 million or something, or 100 million trapezoids? No. Okay. Sometimes people do that and then it'll kind of freeze up because it's too big. Okay. I drew up this unit circle, I guess, in case anybody had any questions. All right. Let's look at this. So let's. These are some just important. We talked about logs and stuff yesterday. So these are just some important little rules with logs. I just want to go over a couple of them with you here. So if you have any log of any base, doesn't matter. If you have log of AB, that you can break that apart into log A plus log B. Okay, so that's sometimes a useful thing to do. Likewise, if you have a log divided by, so if you have log of A over B, they subtract. And that comes from the fact that logs are the inverse of exponents. So it's kind of like when you multiply two things, you add the powers, you divide, you subtract the powers. That's where that comes from, because that's what logs are really the powers. Okay, so and then we talked about the one yesterday where if you have a power inside the log, you can bring that down in front. Okay. So those three are really key to know. And then this is an important one. Log of 1 is always 0. Doesn't matter what the base is here, right? It doesn't matter what base you have, because anything raised to 0, now we wouldn't have a log 0. We would never have a 0 base, right? You can't have a 0 base in a log, okay? Because then that just kind of throws off everything. So all these things are defined with using a positive base, right? This has to be this can't be a negative number either, the base, because again, things get weird when you have a negative base, right? Like if you have -2 and then you try to go to the 1/2 power, well, that's undefined, right? You can't do square root of a negative. So all of these things are defined with the base being a positive value, not 0. So log of 1 is always 0. This is the one that we'll run into most of the time all year long. So that's just something you got to know. ln1, you see ln1, ln1 is 0, ln1 is 0, ln1 is 0, okay? Because that's how we'll usually see it is with natural log. And then the other one is log B, base B is always 1, because this raised to this equals this. So B to the first is B, right? Now where we always see that is with E, because remember natural log is base E. So ln E is 1. So these two we just need to memorize. Okay, ln1 is 0 and ln E is 1. ln1 is 0 and ln E is 1. Okay, you see those? We know those all the time. Okay, all right. So let's say we had a problem like this. So let's say I told you, actually comes out of your book in Appendix E, and they say, let's say right before your calculator battery died, you found these two values. But then now your battery on your calculator is dead, and you now have to do these problems here. Okay? But what I would do is, what we would do, this would be like on a no calculator, maybe kind of a section of a quiz or something. where somehow you'd have to use these values, or it's a multiple choice, you'd have to get the values to be exact, whatever. So this is log base 10, so you were told those two things, okay? So how could we find log base 10 of 6?
Well, we could add those two.
Right, could we think of the 6 as 2 times 3? So we think of the 6 as 2 times 3, and then we could split that into two logs like that. So we could call this log base 10 of 2 plus log base 10 of 3, and then we could just add those two things together, and that would be 0.778, right? Just add those two things together, okay? All right, what about 1/18th?
Just do.
How could we make that
Log,
using just 2's and 3's?
you just do log 2 minus log, or
Now think about the 18. How could you rewrite the 18? 2 times 3 times 3. 2 times 3. So you could go 2. Oh, okay, I hadn't thought of it that way. So then you could just go, okay, so you go, now that's on the bottom, so that's 1 over, I was going to write it 3 squared. Let's do that, but we can do 3 times 3, that's fine. Okay? Now what? What do you do with that? Well, actually, there's probably a step we ought to take first, to be honest with you. What do we do with the fact it's 1 over 18? How about make that to the negative 1? Because then what can we do with that? We can bring that negative 1 out in front. So now this is negative log of 18. Now that 18, we can go 2 times 3 squared, like that, right? Which we can then split up into addition. Now this negative 1 is going to have to stay out in front of that, so we're going to have negative 1 times, and then we can turn it into this addition. So now that would be log 2, and then log 3 squared. Now what can I do with that log 3 squared? Bring that 2 down in front. So that's 2 log 3, which is just what Dallin said. Log 3 plus log 3 is the same thing. And then this would be a log 2, and then there would be this negative 1 out in front of all of it, right? And then there you go. And now we can add, so we 2 of those, so times that by 2, add 1 of those, and then take all that answer times negative 1, right? So you can finish that up. What about log 2,000? What would be the advantage to having 1,000 in there? Because it's a power of 10, right? It's a power of 10. So now we could just do log 2 plus log 1,000. And what's log 1,000? That's 3. So 3 plus 0.301. Right? So just some problems like that. There's going to be some similar problems in your assignment. Just using the log, just being able to mess with the log rules and do some things. Okay, the one I always think of, the one that always comes to mind when I think of as we get later in the year where you have to know this kind of stuff, it always shows up in the no calculator stuff parts. And it always shows up in the no calculator multiple choice, especially in the AP test. Where there's a problem and you work out all this calculus. I mean, you'll work and work and work and work and work and you do all this stuff and you come out and your answer is LN4, right? And you look down at your choices, A, B, C, and D, and there's no LN4. And you're sure you did it right. But guess what one of the answers is? Right? One of the answers is that. Okay? And so you got to know that LN4 is that. Right? So you did all that work. And they really do it on the AP test. They really do a good job of, sneaking those kind of things in where, all within one problem, there's these little different other things that you've got to be able to work at too. So just things like that. Okay, let's do this real quick. Do these last two here together real quick, and then I'm going to let you start working. So let's say I gave you this function here that's 0.3x. So I give you this function, f of x equals 5e to the 0.3x, and I want you to find a couple things. First one, I say, what's f of 20? Okay, function notation is really big. We're going to talk a lot tomorrow about functions and function notation, domain, range, even, odd, periodic, all that stuff with functions. Really key stuff we got to know about. So all year long, everything we do is about functions. So what does f of 20 mean? 20 in for x. So I want to see you get in a habit when you're confronted with this to do this, right? Get in a habit of writing that out. Yes, we could then go to our calculator, but get in a habit of writing that out. If you're then going to type at your calculator, I want to see that on your paper. Okay, so you got that. And now let's say this would be a calculator one. If it wasn't, you would just stop right there. They wouldn't really, never on the AP test do they really make you do a bunch of arithmetic for your answer to simplify an answer. Okay, you may need to do some arithmetic to go on to the next step, but not for your final answer. You wouldn't have to do arithmetic simplification. But type that in, what do we get? 2017 what?
2017.144.
Okay, I like 3 decimal places. Good, right? That's what I was checking to see if you give me 3 decimal places. Would it round? Or is that rounded?
That's rounded.
That's rounded. So 143 would have been okay. What was it? 143 what? 9. So 143 would have been okay. 144 is okay. All right. What about this one? F of x equals 20, find x. Where do we put that 20? On the left side, right? So it's kind of like input and output. Functions have input. That's what you're going to hear me say x and y usually. Say input and output. So here the input was 20, which is your x. Here they're saying the output is 20. So when you see f of x equals 20, they're saying the output is 20. So we got 20 equals 5e to the 0.3x, and now we have to solve that. So let's do that 2 ways. First, let's solve it manually and then type into our calculator. So what do you have to do next? Divide by 5, because you might get this on a no calculator. So let's pretend this is a no calculator right now. So we would put the 20 there, we would do this, then what? You could go right to ln form, or what I typically do is the ln of both sides. Now some of you are going to say, why do you do that? That seems like a little extra work. You might be right, but it works all the time, even in some little harder ones. I do the ln of both sides, but you could also just turn it right to ln form. ln 4 equals 0.3x, because that's what's going to happen here. That's what's going to happen right here. Because what am I going to do with this power that's in this log? I'm going to bring it to the front. So I'm going to have 0.3x, and now I'm left with ln e. Well, what did we just say ln e was? ln e is 1. So since ln e is 1, I end up here. So yes, was that an extra step? Problem. Okay, so if you want to go right to there, that's fine. We got that. And then what? Divide by 0.3. So ln 4 divided by 0.3. It seems weird to leave that as that, but you could say that's 3/10, so you could divide by 3/10 and be times by 10/3. You could make that 10 ln 4 over 3, whatever, don't care. So this is no calculator. We would just stop right there. Okay? All right. Or we could go to our calculator, and this is perfectly allowed. If this was a calculator problem, one of the 4 things you could use your calculator for is to solve an equation. So once we got to here, we could go to our calculator. Let's all do it. Jaden will present that for us. Let's go to on our calculator screen. Let's go to algebra, solve. Okay, and let's type in 20 equals 5e. E's right over here to the 0.3x. Notice how that e looks different than the e you would get down here. Okay, that e is kind of bold and kind of a different font. And then don't forget we have to do a comma x there at the end. Hit enter. Since we got a decimal, it should just do it. Now do ln 4 divided by 0.3 for me, which is what we just got a minute ago. Oh, you did it already, didn't you? You did it right here. Okay. Notice how, yeah, you type in ln 4, how it gives you 2 ln 2. But yeah, ln 4 divided by 0.3, look at that, same answer, okay? So we would give that as 4.620 or 4.621. Okay, so you're going to have some problems like that. All right, let's get to work. Appendix E is exponentials and logs, and then appendix G, but skip 1 and 5 on appendix G. Okay, so again, it's on that assignment sheet. Who needs an assignment sheet? Who wasn't here? Did I handle that yesterday? Anybody need this? Anybody's got this? Okay. All right. So on appendix G, skip 1 and 5, and then do appendix E, those evens.